Okay, good. So this is going to be lecture 3. So the previous lecture, basically what we saw was some of these sort of basic ways of de-randomizing algorithms. The first one was this method of conditional expectation that we saw, which is like if you're able to estimate your partial decisions and how good these partial decisions are, basically based on you've made certain decisions so far, and the next random bit, if you have some way of saying, from this point onwards, if I behave randomly, what sort of reward am I going to get? And if you have a way of estimating that well, then you can use that as a way of getting a pretty good, removing the use need for randomness at all and just going down the path that seems to give you better benefit. The other method was this thing where you basically say that, if your proof as to how well your randomized algorithm was performing was something that depended on very few variables at a time. A classic example of this was the max cut situation. In the sense that once you use linearity of expectation, you're really looking at something you're just looking at what happens edge by edge. And as far as the edge is concerned, you only care about two of the decisions, the two vertices that is there. And similarly, this in general shows up when you want to you're dealing with these what are called constraint satisfaction problems, like max sat or anything of that sort. So as long as each constraint is somehow very local, there are many times when you can get away with something like limited independence. Okay, that was the broad idea of why we went down this path. But last time we just for pairwise independence, we gave an explicit construction, which was very convenient and so on. And we somehow said that, hopefully 3-wise independence, 4-wise independence, there should be good constructions. So today, most of the lecture is going to be to construct these families. Okay, so that's going to be a bulk of this today's lecture. And once we build these constructions, we are then going to see how we can apply it in, let's say, other setups, like for example, sampling and so on. I will have very little, depending on how much time we have left in today's class. I might do a little bit of this, but then push the rest of the discussion to the next class. And hopefully by today evening, I will also put out the first problem set. And as mentioned earlier, I suspect the last couple of questions in the problem set, you may not have the background right now to solve them, but hopefully you will have the necessary background by after Thursday's lecture. But at least the first few questions you can start solving. Okay, so let's start with the definition and what we really want. So what is a hash family? It's a bag of functions, and usually you have a certain input domain and an output domain. So typically we'll call them capital N and capital M. And the standard terminology that is also used in Vadan's manuscript is that you should always think of capital N as 0, 1 to the small n. So capital N is like 2 to the small n. So, okay. And in general, what I have described here is the notion of k-wise independence. But you can mentally instantiate k equal to 3 or k equal to 4 or something, just something that makes things concrete. And what is this saying? That you say that a bag of functions forms a k-wise independent hash family if the following two property holds, but technically speaking, the second property implies the first property. But it's good to have this in mind, both of them. Okay. And what's the first property? The first property says that suppose you fix a certain coordinate x of your interest, but then just imagine choosing the function h at random from your bag. If you look at the marginal distribution of what is this function assigned as the value for x, that should look completely uniform. So I've just written it to say that if you have a specific output in mind, the probability that on this particular input it takes this particular output is just 1 over the size of the output. Okay, and it's important that this probability is only over the choice of the function h. This should be true for every choice of x and for every choice of epsilon. Every choice of alpha. Okay, so the randomness is with respect to you choosing the function. Once you choose the function, this function specifies the values on all points x in the input domain n. Okay, good. And so this is just saying that, it marginally it looks uniform. Like on every single coordinate, it looks uniform. K-wise independent is saying that the same thing happens even if you look at a window of at most k different input coordinates. Okay, so in other words, if you say that, suppose you have a bunch of distinct x1 through xk, and you have some specified output values you want them to take, alpha 1 through alpha k. Alpha 1 through alpha k need not be distinct. You might want the x1 and x2 to take the same value, maybe x3 and x4 to take some other value, etc. But what you want is, once you specify k distinct coordinates, those k things taking any specific value should start looking like 1 over m to the k. That is, this is what will happen if you assign each of these values completely at random. And you want this property to hold as long as you are looking at a window of size no more than k. Okay, so that's what k-wise independence is. Now, often what we might want is, we might want to find an explicit h that is sort of as small as possible. Like, I don't want this bag of functions to be too large. And the reason is because many times your choice of randomness will be with respect to choosing this function, and I want to expend as few random bits as possible to choose the function. That's why you would want this bag to be small.
In fact, the whole point of de-randomizing
would be rather than choosing the output values of x, I'm going to just choose the function at random and let it determine the output values of all these x's. So that's typically how you go about doing something like this. Okay, and so therefore you would want this bag to be small. But notice that the fact that you want a probability to look like 1 over m to the k immediately suggests that your bag must be of size about m to the k. Because you want only one among this big bag of functions to sort of satisfy this or something like that. So there is some dependence on n and m that is going to show up. And at the moment, it's unclear what sort of dependence on n and m is going to show up. You should mentally tell yourself that as long as it's something like m to the k, which seems to be somehow the necessary requirement for this, something like this should hopefully be accepted. Okay, so this is what we are going to aim for. That we want a bag of functions that is not too large, that satisfies these properties. Okay, so I hope the definition of what we are trying to build is clear. Okay, good. So, we saw just a case for k equal to 2 in the last lecture. We gave an explicit construction of k equal to 2, and also in this regime where the output domain was just 2 elements. So what we are going to do is, we are going to focus on that, try and abstract it out, and sort of see how do I generalize it to maybe larger domains or larger k, etc. So we're going to try and do some sort of generalization, and hopefully that will lead us towards constructing these hash functions in general. Okay, so let's look at a special case where this was the hash function that the hash family that we described last time, where each function in the family is specified by something like t bits, and t is like about log n. And we identified the set of n elements, which was the input domain, to be non-empty subsets of these t variables. Okay, I don't know if I used k in the previous lecture, but I'm using k for independence, so I'm just trying to find some other letter for this. Okay, so the important thing that's going to be, like, in order to specify a hash function, I now need to tell you what this b1 through bt are. Once I tell you what b1 through bt are, you know the truth table of the hash function, so to speak. You know its values on all the endpoints. Okay, and so we are going to try and look at this construction and sort of say, okay, fine, this gave a very simple construction when it came to k equal to 2, where it gave us pairwise independence. Suppose I wanted to build higher independence. What should I do? What was the property about this that we really ended up using? And how do we generalize that to higher independence? Okay. So it's going to be, this might feel a little weird, but it's whenever you see a bunch of things like this, it should hopefully start making you think about it in this direction. The sense that the function somehow seems very linearish. It takes a bunch of bits and then it keeps on taking some XORs. So it looks like a bunch of linear operations that are going on there. So let's try and write it a little differently. Okay, so I'm going to think of B1 through BT. This is some input vector that I have. And what did the output actually end up being? So let's, for the sake of completeness, I'm just going to look at B1, B2, B3, so that we can concretely write down what did we output. If once you give B1, B2, and B3, what's the truth table that you ended up outputting? Okay. So we ended up outputting this big list. For every non-empty subset, we outputted a bunch of parities of them. And I can always write this as the following matrix: 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, and 1, 1, 1. And this is the, I don't know, the 7 length output that you end up computing. Okay. So this is like a 3 cross 7 matrix over F2. And in some sense, the hash function almost looked like this matrix vector multiplication. There is a particular matrix I have in mind, and my function was specified by choosing what was this 3-bit vector that you have, and whatever I multiply to this matrix, I'll get some large row. I'll get a row of 7 things. I just say that's the truth table of my hash function. Okay, this is just a slightly different way of just expressing what happened. Okay, so the first one, notice, is just the parent is just B1. Second coordinate is just B2. Third coordinate is just B3. Fourth coordinate is a parity of B1 and B2. Blah, blah, blah. Okay. Okay. Now, what is the key property of this matrix that makes this output a pairwise independent distribution?
Is the Hamming code?
Yeah. This good. So this should already start telling you that there is something about the matrix that makes it a good pairwise independent distribution. And it seems like this is like the matrix somehow related to the Hamming code. And so hopefully there is some connection between codes and hash functions. So this is something we will do at a later point. But in this case, what is it really that made it work? So what did we want from our we wanted to basically say, suppose I focus on just 2 of the coordinates and I imagine picking B at random. I want to say these 2 coordinates should look random. So let's forget about the rest of the matrix and just focus on 2 coordinates. Okay, so I have in this case B1, B2, and B3. So maybe I'm just focusing on this coordinate and this coordinate. That maybe corresponds to looking at just these 2 column vectors. So I'm like looking at this matrix and multiplying it with this, whatever, those 2 column vectors, whatever are the relevant column vectors there. And at this point, I'm going to end up with 2 coordinates. And what do I want? If these were completely random, I want this to look completely random. I want the output, all 4 possibilities, to happen equally likely. Okay, and let's ask ourselves, what sort of column vectors will satisfy this property? So the important thing is that this must have rank equal to 2. That is, it must be full rank. That is, if the columns are linearly independent, then this is like it's going to be a surjective map into whatever is the output space. And linear maps have this nice property that every output that is achievable will actually be achieved with the same size. So it sort of nicely ties out the whole thing. So the property we want from the above matrix is that no matter which 2 columns you end up choosing, you want those 2 columns to be linearly independent. Because it's 2, linearly independent just refers to the fact that I want the 2 columns to be different. Okay, so what we want here is, all I want is some matrix that has the property that any sort of k columns that you care about, if you want k-wise independence, you want to make sure that any set of k columns must be linearly independent. If you have that property, then this is in some sense like a formal proof to tell you that the resulting distribution will indeed be k-wise independent.
This is equivalent to the code having distance greater than 2.
Good. So I haven't said more about what codes, etc. is, but you can imagine that, if you think of this as either a generator matrix or a parity check matrix of a code, it sort of is going to tell you what are properties of this code that you need. But yeah, you're absolutely right. There is a strong connection between what you want here and what codes are. Okay. So is this sort of rough argument clear? Okay, so this basically is going to now lead us to sort of say, if you want to generalize this to higher K, the problem now boils down to finding matrices of this property. I want a matrix, hopefully that has far fewer rows than columns, because the number of rows is going to dictate, in some sense, the size of this bag, right? Because in some sense, that's what is going to tell you how many different hash functions I have. I'm going to have one hash function for every choice of B1, B2, B3. So I want there to be as few rows as possible, but I want something over few rows, lots of columns, with the property that no matter which K columns that you end up taking, I want them to be linearly independent. Okay. And if you're interested in outputting bits, maybe you want this over F2, something of that sort. But let's maybe ask a simpler question. Let's ask the same question as over rationals or reals, just to get a feel of it. And then we can focus on the actual question at hand. Okay, I want a matrix. I'm thinking of these matrices as real valued matrices or something. And what I want is I want a few columns, but lots and lots and lots of rows. Sorry, few rows, but lots and lots of columns. With the property that, I don't know, any 5 of them are linearly independent. Okay, so do you have matrices of that sort that you have seen in other places? Okay, no, not codes. Let's do like very basic this thing. I don't know what BCH codes are. Yeah. So, what are invertible matrices you can think of? Identity is one example, but that there's only n of them. Random. So there should be a, okay, so one of the questions was, can I randomly just choose a matrix? That would also work. In fact, this is the reason why it will turn out that a random choice of a matrix would satisfy this property. And therefore, a random function will be a k-wise independent hash function. Like a random, whatever function you create this way will be k-wise independent. So this sort of tells you that these hash families are pseudo-random. But we are trying to construct them in some deterministic fashion. We are trying to find an explicit set of functions that have this property. So one matrix that works is this matrix called the Vandermonde. Okay, so you just have 1 alpha 1 to the k minus 1, blah blah blah, 1 alpha I to the k minus 1, and so on, as many as you want. And what is the property that these matrices have? If you take any k columns, those k columns correspond to some choices of alpha 1 through alpha k that you chose, and then you picked up the k cross k Vandermonde matrix. And as long as these alphas are distinct, this matrix is going to be invertible. Okay, so in fact, over reals or over like any infinite field, you actually can construct a matrix with infinitely many columns that has this property that no matter which set of k columns that you end up choosing, they will turn out to be linearly. Okay, so this is the Vandermonde matrix.
Oh, this would also be true for a large field. It's not necessary.
Yeah. So, okay. So the natural thing is, okay, why not we use the same thing for F2? Okay, and the main problem is, alas, F2 only has 2 elements. Okay, but this should be a matrix that we should try to get towards. I want to build a Vandermonde-like matrix. Okay, I want to somehow cook up this thing that, you know, any bunch of k columns are linearly independent as a Vandermonde-ish sort of structure. Except that if I'm working over F2, I'm sort of stuck because I only have 2 elements, which is 0 and 1. So we somehow need a way of making our field larger so that we can work in that domain and build the necessary thing that is needed. Okay, so I'm going to take a short aside because I don't know how many people here have had exposure to finite fields, etc. I'm almost going to prove nothing. I'm just going to tell you what you need to know, and we'll just focus on that. If people are really interested, I can just add a reference to some primer on finite fields. But what we need, I'm going to just write down, and which is hopefully make things quite clear. So what is a field? It's basically where these matrices sort of live in, right? And like these matrices, the entries come from some field. And what's the underlying expectation of these things? I mean, you just want the domain to be something that you can add, subtract, multiply, divide. Obviously, you divide only by things that are non-zero. Okay. So things like your rational numbers or real numbers, complex numbers, these are all what fields are. And they satisfy a lot of very, very nice properties that we often almost just take for granted. Many times we just assume that these sort of properties hold over other domains, and we're often surprised when they don't. Okay. So this is what a field is. And something that we'll deal with most of the time here is often a finite field, because we are often working in some sort of a discrete domain. We want some finite domain. So the canonical concept finite field is basically you pick a prime P and then take a set of possible remainders modulo P and just do all your arithmetic modulo this prime. Like whenever you want to add stuff, you add stuff and go take the remainder. If you want to multiply, you multiply, take the remainder, etc., etc. Okay. So turns out you can generalize this notion to a bit more, where I'm going to create a field of 4 elements. Okay, and I'm going to call them as 0, 1, x, and x plus 1, where the prime that I'm thinking of is x squared plus x plus 1 over f2. So this polynomial x squared plus x plus 1 is prime in the sense that it doesn't split into two smaller factors. It sort of is irreducible over this thing. So I'm going to use the same intuition and sort of say that, okay, let's think of these as my 4 elements. Now notice that because this is a polynomial of degree 2, if I ask what are all possible remainders you could get, well, it's going to be any degree 1 remainder. And these are the 4 things you can get over f2. It can either be 0, it can either be a constant, which is like 0 or 1, or it can be x plus 0 or x plus 1. Okay. So, and now the point is, I mean, like obviously adding these things, etc., become clear. When you add stuff, the polynomials are like you add these polynomials. We now need to get a sense of what does multiplying them mean like. What is x times x? So, of course, this is equal to x squared. But again, whenever we do operations, we are going to do operations modulo this polynomial. Okay. And notice that x squared is the same as x plus 1 mod this here. So when you multiply x and x, it's like you get x squared. So similarly, you can try out all the other, you can sort of write your multiplication table in some sense, and you can easily see that this actually gives you a field. In fact, you can convince yourself that the inverse of x is actually x plus 1. This will turn out to be equal to 1 mod x squared plus x plus 1. Okay. We are working over f2. So whenever you see a 2, you just make it 0. So plus x minus x is all the same. So, okay. So now we have just built a field over 4 elements. Okay. So there are these prime fields and there are these some sort of special fields, which are not prime, but somehow they seem to be related to primes. They're built the same way. Okay. And turns out that in general, you always have a field of exactly p power r elements, where p is a prime and r is any integer of your choice, positive integer of your choice. Okay. And you build this field in the same way like I just did. You find a polynomial of degree r that is prime, in the sense that it's irreducible, and then do all your operations modulo this way. Okay, and turns out you will end up getting exactly p power r elements. It's not hard to show that this is a field, etc. And it also turns out that there are plenty of primes of every degree over fp. So in some sense, for every choice of r, there are mu's that you can choose, which will end up giving you a field of this much size. Okay, and notice that because the elements are polynomials over whatever is the base field you started off with, as far as addition is concerned, it's like as if you're adding polynomials. Okay, so the field is like it's a vector space over whatever you started off with, except this is something that in addition to it, you have a notion of multiplication of vectors. Okay, so you have something more than just saying that this is So basically you can think of f p power r as just consisting of r length vectors over fp, or you can think of it as a field on p power r elements. Okay, so something that we will not need, but I'm just going to mention here, saying that these are all the finite fields. That is, there is no more. The only sort of finite fields are either things of the form fp power r, which is built in exactly the same way, and also for every p power r, there is exactly one such field. The sense that once you fix your field size, there is really just one field of that size. By definition, it somehow doesn't feel so, because it feels like, maybe you wanted to pick a field of size f8. So how do you build a field of size f8? You will choose a degree 3 polynomial that's not irreducible. Maybe you chose a degree 3 polynomial that was not irreducible. Somebody else chose a different degree 3 polynomial that's not irreducible. So on the face of it, it feels like these will generate two different things, because their multiplication tables are going to be different. Okay, but it turns out that if you rename your elements appropriately, it turns out the both of them are looking at the same thing. So it's a surprising fact, but we won't need it really. But it's just that, so often whenever we talk about there is a field, I'm going to construct the field of size 2 power r. It makes sense for me to say I'm going to construct the field of size 2 power r because there is just one r. We'll just choose a representation that is convenient for us. Okay, so this is what a finite field is, and this is all that we are going to need mostly for the rest of the course. I don't think I need anything more besides the fact that there are fields of size f2 power r that you can construct. All right, so now let's go to k-wise independence. We're going to try and build some hash functions. Let's forget about exactly what our domain of it, what our input domain and what our output domain was. At the moment, I want to build something. Okay, and then later we will try and add bells and whistles to get the right size and so on. Okay, so I'm going to basically try and use the Vandermonde matrix. Okay, so what Vandermonde matrix? First thing I will do is I'll pick an R, because I need there to be n columns. Right? If I'm interested in functions that go from an n-length domain to something, I probably want something to have n columns. So I'll choose a field large enough such that I have n possible columns in my Vandermonde. And in my Vandermonde, what do I want? There is one column for every field element. So let's just pick an R such that you have a field of size that is just a little bit larger than n. Okay, this can just be greater than or equal to. Okay, in that case, maybe ceiling of log n is sufficient. There's no +1 needed, but I'm just putting it in.
Every field greater than n because one element.
Oh, you can't take zeros. Good. Yeah. Okay. Good. Thanks. Okay. So okay, and let's take alpha1 to be distinct non-zero. Actually, even if it is 0, it's okay.
We have a 0 columns.
No. The Vandermonde always starts with 1. So you'll get 1 0. So I think it's
but 0 is 0 power 0 1.
Huh?
It's 0 power 0.
0 power 0 is 1. Yeah. Okay. And what's the function going to be? So I'm going to take b1 through bk. This is my vector, and this is going to be 1 alpha 1 to the k minus 1, 1 alpha n to the k minus 1, and this will obviously spit out an n length vector. Okay, so in some sense, this is my mental picture of what these maps are, but maybe it's convenient to write it as what is your map really doing. So given this, so this HB at a point alpha, this is just going to be you look at this van der Waals matrix, okay, but focus on just the column corresponding to alpha. I'm not writing it properly, but I hope you know what this means. This is like, forget the matrix and just look at that one relevant column, okay, and take its inner product with B. Okay, so this is the same thing as saying this is summation bi alpha to the I, where I goes from 1 to, sorry, maybe alpha to the I minus 1, I goes from 1 to k. Okay, so that's what this map is. And in fact, this is a map that's really from f whatever 2 to the r to f 2 to the r. Okay, there's a question in chat. They're saying are the BIs also in FQ? Yes. I mean, I'm going to specify a hash function by specifying what these B's are from the field F2 to the R. And once I specify this hash function, it tells me a way of building this large, whatever, row vector. Okay, so this is my bag of functions. As you vary over B's, you have different choices of these functions. At the moment, they are from the same input domain to the output domain. Okay, so you can think of this as your capital N. F, like 2 to the R is your capital N. So you have a map from N to N. And as you vary B's, you have different hash functions that you can get. Okay, is the function description clear? Okay. So at the moment, what we seem to have is like we have built a k-wise independent hash family from basically 0,1 to the R to 0,1 to the R, where R is like roughly about log n. Okay. And what is the size of this hash family? Well, the hash family depends on the different possibilities I have for the choices of B1 through Bk. Each one has 2 R choices, and I need to choose k of them. So the size of my family is about 2 to the Rk. Okay, which is like n to the k. And it's like the sort of, it felt like the right order based on just the definition, because we were saying that if your output domain is capital N, then, I mean, you need the bag to have at least n to the k elements. And this is saying that, okay, just about n to the k is actually enough. Okay, good. So let's look at, I mean, even though we have seen this, very in a sort of hand-wavy way, let's just focus on this once and sort of convince ourselves that whatever we have built right now is actually a k-wise independent hash family. Okay. Now, what do we need to do? I need to basically say fix some distinct x1 through xk. Okay. And you tell yourself that I want the hash function to take value beta I at xn. And I want to know what's the chance that that happens. Okay, I pick a function h at random. What's the chance that x1 takes value beta 1, x2 takes value beta 2, blah, blah, till xk takes value beta k. Okay, this is what we want to know. And this is the same thing as saying that if I look at h of x1, I mean, there is a b sticking here, hb of xk. I think of this as a vector. I should be able to write this as some matrix vector product or something, right? So is there a way to describe what should go here? I mean, this is equal to what? So I basically just take B1 through Bk and then just focus on the k cross k van der Waals, where these are the columns indexed by, I don't know, x1 through xk. Right? That's basically this was the definition of what HB of xi was. So therefore, this k length row vector is same thing as this row vector times this matrix. But we just know that this matrix is invertible. So which means if I ask myself, what should B1 through Bk, what are possibilities for B1 through Bk for this equality to hold? I mean, this is what my, whatever, beta 1 through beta k are. Okay. Well, because this is an invertible matrix, there is precisely just one choice of B1 through Bk that can actually give me this. So of the 2 to the RK choices, there's just one choice that works. So therefore, the probability, whatever, for star holding, this is exactly 1 over 2 to the RK, which is like 1 over whatever is the output domain for RK. And that's what you wanted to prove when you say that something is k-wise independent. Okay. This is proving property 2. Notice that this just means that property 1 also holds. That is, if we focus on one coordinate, of course, it will look uniform. Okay. So maybe this is a good point to pause and find out if there are any questions, if there anything that's unclear. Okay, maybe it's a good thing to sort of take an alternate perspective, which is basically whatever is written here, it's often convenient to think of it in this other way if it helps. Okay, which is one way to imagine this is that every hash function was given by k coordinates. I'm going to mentally think of myself as these k coordinates as the coefficients of a polynomial of degree k minus 1. When this is a polynomial that I'm basically focusing on. Okay, this polynomial. Okay, so I don't know why I missed this. Okay, so in some sense, what is your hash function saying? The function is specified by a polynomial b. And what's the value you take at a certain x? Well, you just evaluate this polynomial at x. If you notice, that's precisely what a Vandermonde is supposed to do. The coefficients are given, each column corresponds to something that looks like 1x, x squared, blah, 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 till x to the k. So the inner product is precisely the evaluation of your polynomial at the point you care about. And why is it k-wise independent? And this just comes from your interpolation that you may have seen in other places. That's also Vandermonde. So one way to tell this is that if it's a degree k minus 1 polynomial, there are k unknowns, which are the coefficients. And even if I tell you k of the evaluations, like the k minus 1 of the evaluations, the kth evaluation still looks completely random to you. Another way to look at it is like no matter what someone says is the kth evaluation, you can still construct a polynomial. Yeah, this is what is exactly used in secret sharing and so on. So you can either think of it as saying that the Vandermonde matrix has a certain property, blah, 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 it works. Or you can tell yourself that, look, what this hash function is really doing is telling you the evaluation of the polynomials on many points. Obviously, many of these points are correlated. Like if I have a degree 3 polynomial, once I know it on 3 points, I know the polynomial exactly, so I know it on all the other points. But this is just saying that as long as you look at 3 or fewer points, they will look completely random to you. So that's an alternate perspective of what these hash families really are doing. You're just focusing on the correlation between different coordinates coming from evaluations of the same polynomial. Okay, so I hope things are okay so far, and this gives a way of building hash families from, in some sense, the same input domain to the output domain. Okay, good. So now let's finally go to let's wrap this up, which is to ask, maybe my input domain and output domain are not the same. Okay, fine. Let's admit that the input domain and output domain, let's say they're both powers of 2 to make it convenient. Okay. But I maybe want something from 0, 1 to the end to, I don't know, maybe 0, 1. Okay, I don't want it from 0, 1 to the end to 0, 1 to the end. So how do I build these sort of functions? We're just going to say that no, given any hash family, you can always massage them to get other sorts of hash families in some stupid ways. Okay, so I'm going to, from this, sort of tell you how to get functions from 0, 1 to the n minus 1 to 0, 1, and also from 0, 1 to the n to 0, 1 to the n minus 1. Maybe it will be wasteful in the sense that I will be using the same amount of randomness, but at this point, n to the k was something we were anyway willing to afford. So now we are going to try and get n to the k even in these sort of situations. And both of these are sort of completely trivial. So maybe the one on the right is easier.
So you're saying you are doing this generic.
In a very generic way. I'm not going to be clever about it.
Previously, there was like an obvious, because you had this F2 to the end. So there's a vector space. You just
Yeah. So that, but here, this is just something I'm just going to do in a very generic thing. There's nothing fancy going on here. And like Srijato mentioned, what do you do? Okay, maybe I should call it a different function. Okay, maybe I'll call this tilde and this as hat or whatever. I mean, these are two functions that are built out of the h that we started off with. And how do you build h hat? Well, you just compute h and just drop the last bit. Okay. Compute h and drop the last bit. Intuitively speaking, you should convince yourself that this will still remain k-wise independent. Because even with the last bit, it was k-wise independent. So if you drop the last bit, the number of collapses is going to be roughly the same. You just need to spend a moment's thought to convince yourself that k-wise independence will be preserved when you do this. Okay, what about h tilde? How do you build h tilde?
Randomly sample the last bit and
I don't want to use randomness here. I want to build this bag. But again, you don't need to randomly sample. Just put 0 at the end or something. Okay, just return h of whatever x, where you just pad it up with 0. Okay, because in some sense, the k-wise independence that you need from h tilde is actually less than the k-wise independence you need from previously in h. You also want the coordinate x0 and x1 to look independent. This way, x1 is never going to show up here. I'm only interested in things of the form x0. Again, you should convince yourself that this will also preserve k-wise independence in general. Okay, both of these are really stupid operations. You're just basically forgetting information that your original h had. Okay, so I'll leave you to check that these preserve k-wise independence. It's not hard at all. It's just like once you notice it, you'll just be like, oh, this is obvious.
So here you're assuming that you're given the topic and how.
Yeah. So
I thought you were asking the way, because in the previous case, you showed, strictly speaking, how to get a hash function
from n to n.
F to B, from
F to F in general.
Yes. Yeah. But you didn't show it from 0,1 to the end to 0,1 to the end.
Yeah. So for 0,1 to the end, I'll just think of F as being F2 power something.
That's all.
Yeah, right. That's exactly it. And right now, the only thing I'm doing is like, decoupling what the input domain and the output domain is. That's what we are doing here. And we are doing it in a rather silly fashion. So just forget information and it's perfectly fine. So basically, this tells you that if someone gave you a family from n to m, you can always build a family from n prime to m prime as long as n prime is smaller than n and m prime is smaller than n. Just by dropping the whatever the right set of coordinates.
So in the first one, why did you drop all but one of the coordinates? Did you mean 0,1 to the end?
Oh, sorry. I meant 0,1 to the m. I mean, this was to sort of say shrinking the input by 1 and shrinking the output by 1. That's what I meant. Okay. So therefore, now what we have, this basically completes our construction of hash families, which is to sort of say, if you care about hash families from 0,1 to the n to 0,1 to the m, you should think of this as capital N and this as capital M. Then you can construct k-wise independent hash families where the size of this bag is roughly like the max of these two quantities power k. Okay. Good. Okay. So this is the construction that we have right now. And one way to think of this is to sort of say, to specify a function in this bag, I need to basically tell you k times max n comma m many bits. That's how many bits is needed to tell you what one function is.
Normally you pick how many in.
I mean, if the function was completely at random, I sort of for everything in 0, 1 to the n, I need to tell you m bits. So it will take m.
So m gets reduced to k.
No, it's like m into 2 power n times n.
If you like look at it as a function.
Yeah. But nevertheless, this sort of, this is just the max of n comma m. And then there is a factor of k that is on the outside depending on what sort of independence you want.
So, but then we are able to get n-wise independence using n squared bits, isn't it? No.
Sorry, why
I'm plugging k equals to n here. We get n-wise independent.
No, you're looking at, I mean, n-wise independence is still limited independence because the number of coordinates you have is 2 power n.
Okay.
Right? I mean, for every choice of 0, 1 to the n, you have a coordinate in substance. So the truth table is of size 2 power n. And it sort of tells you that you can get these things with about max of n comma m, the input length of n comma m raised to the power k. Okay. So if you think about it, okay, this is an upper bound, but it's unclear if this is also a lower bound. Because if you recall, what happens when k equal to 2? The number of bits you actually, the size of this hash family was just actually equal to max of n comma m. In that case, m was equal to 1. So you somehow managed to get away with just like something like n plus 1, a bag of size n plus 1 or something. Okay. So you might ask, what is the right dependence here? What's the right upper bound and lower bound that you need to have? These are great questions to ask, and which is why, sorry, I cannot understand why I need k times max n comma n to specify. I think there is a confusion between max versus log. I mean, the input domain is 0, 1 to the n, which is, I mean, this is like.
No, it should be log, right? Because the size of h is that, right? So you need to, if you want to specify a function.
Yeah, so this is capital N and this is capital M. So in order to specify a function, I needed to specify k elements of my input domain. And every element of my input domain requires log of capital N many bits, which is small n, right?
No, okay, I'm also not confused. So go down.
Okay.
The hash family. So the total number of functions that you have is of size what you wrote there, right? Like the size of the hash family, the size of the family is max n comma m to the power k, right? Then, I mean, to specify one member of the family.
Oh, sorry. No. I seem to have made a mistake here.
Yes.
Okay. So, what do I need to specify? I need to specify k elements of the larger field. So I should basically have written max of capital N comma small n to the power k. Yeah, thanks a lot for pointing this out. Yeah. So in the sense that in order to specify a hash family, I needed to tell you k symbols from the domain. And each symbol, like you can either say it takes small n many bits to represent, or if you want to count the size of this family, then it is like capital N. Yeah.
So
thanks.
K times log of that, which is equal to k times.
Yeah. So it's k times log of that, which is now log of capital N is small n. So therefore, okay, good. So just to wrap things up with one example is just that, if you now wanted to go back to your max 3 sat, we mentioned how you can de-randomize it using the method of conditional expectation. Now you know how to construct 3-wise independence. So you could also just build a 3-wise independent distribution and just try it on all of those points alone. And there are only going to be n cube points. So you need to try out on n cubes things, and then you'll get another way of de-randomizing max 3 sat. I mean, we did mention it last time, but now you know all the missing parts, everything that goes into it. So just to summarize, so what we have right now is that there are explicit k-wise independent hash families from capital N to capital M that have size about capital N plus capital M to the k. Max, I've just replaced it with capital N plus capital M. Okay, I'm ignoring 2 to the k sort of factors. I'm thinking of most of the time when we are applying these things, we're thinking of k as a small constant, like I don't know, 10 or something like that. Okay, any questions so far?
So here, what do we get when from this construction for 2 byte independent? What is the
So this will tell you that the hash family has size n squared. Whereas what we actually got was a hash family of size something like n plus 1 or something.
But these construction for k equal to exactly use the head amount code, right? Shouldn't they match?
Yeah, so the thing is, right now, we like in the lower bound look like 1 over capital M to the k. Whereas now I'm sort of saying capital M plus capital M to the k. I'm sort of ignoring the difference between capital N and capital M.
But the weakness is reference in the analysis.
Yeah, it's in the analysis.
Equals to it gives us
So in the problem set, you will actually prove a lower bound and see. I mean, I don't know if we have constructions that match the lower bound, but you'll prove a lower bound where this k will be replaced by k by 2. Then you can get a lower bound. In the sense that capital N to the k by 2. Which was not something that you got from the definitions.
I think BCH codes give you the 8 power k by 2 construction.
Oh, right, no, BCH codes do.
Because there is
Yeah.
You only need to do it alpha or
Yeah, right. So we do have matching thing, but this is like in some sense this is like the Reed Solomon version of it.
Yeah,
And,
I mean, if you don't expect this alpha is in a basis of f to you.
Yeah. Okay, so this completes the construction of these k-wise independent hash functions, and I'm going to maybe take about 10 minutes to tell you a little bit about how are we going to use this in samplers. Okay, and see what we get. Let's just again recall what a sampler was. Okay, so this is something I'm sure I'm going to make a mistake later on. So I realized that in Vadan's notes, he always calls them delta epsilon samplers. And I would have mentally put epsilon first, but some of these are called delta epsilon samplers. I was also trying to get a sense of why would I put epsilon first? I don't know, like D, E, alphabetical order, delta epsilon probably makes sense, but something. Okay, but okay, this is what a delta epsilon sampler is. Let's forget about so epsilon is going to refer to the accuracy, and delta is going to refer to the probability error. Okay. So what is the goal? You're going to be given some oracle access to a function f. I'm going to think of it as either 0,1 to the r or 0,1 to the m or something. I might end up changing these letters also. Okay. And what do we want? We want some algorithm that has query access to this function f. And the goal of this algorithm is to estimate the expectation of f. Where the expectation of f is you just pick an x at random and ask what is the probability that f of x is equal to 1. Okay, so I have specified it as the function output being Boolean, but you can imagine the same situation perhaps holds even when the function output is a number in 0 to 1 or something. Okay, but I'm just trying to work with what perhaps is the first thing you might want to build your definition on, and we might later generalize it to other. Okay, so what is the guarantee that we want from this algorithm? So the algorithm with whatever oracle access to f will do something. It might toss a bunch of coins, decide to query this function f at various places, etc., etc. And those are some random choices that the algorithm A will make. So depending on those random choices, whatever this outputs, I want it to be within an epsilon error of the correct value of mu of f with probability at least 1 minus delta. Okay, so this is what we mean by I want a sampler. Rather than, maybe not rather, I mean, like an obvious sampler we have in mind is this basically query the function at t locations for some choice of t and just ask, how many things did turn out to be 1 and how many turned out to be 0. Basically take your empirical average and output that. Okay, and how do you normally analyze these things? Is there for some reason for the additive reason to have additive error and not multiplicative? I don't exactly know, but this is, I mean, it's more like yeah, exactly. The Chernoff bound is nicer when written this way.
That's the mu is constant anyway, they translate.
Yeah, I know, but I guess the point is also that if you can maybe think of mu as being sub-constant, in those situations, maybe multiplicative error might be better. But unfortunately, Chernoff will become Poisson and things will get a little messy. So it's just that I've just written the version that is most suited for applying Chernoff mode. That's it. Okay. So what would you do here? You would basically define a yi, which is the indicator random variable that whatever f at whatever the ith query returns 1. Okay, and you're basically going to ask, okay, I know that the expectation of summation yi, this or 1 over t times this, where I goes from, let's say, 1 to t, this is exactly equal to mu. Because every yi, there is a chance of, I'm assuming that the ith query is completely at random, since we are looking at a random sampler thing. And so I know that every such yi is an indicator random variable, which turns up 1 with probability mu and 0 with probability 1 minus mu. And what are we interested in? We are basically interested in how much does this deviate from the expected behavior. And this is exactly what Chernoff bound is, right? Which is that it just says that, if I'm actually giving a simpler version of Chernoff bound probably, which is perhaps easiest to prove. Suppose you have y1 through yt that happen to be independent random variables that take either value zeros or 1. So there's some Bernoulli random variables. And I'm also told that every yi has expectation, the same expectation, which is mu, basically identically distributed. Okay. And this is your empirical average. That is, you make a bunch of samples and then you take the average that you see within those. And you're going to ask, what is the chance that your average, the empirical average, deviates from the correct expectation by more than epsilon? Okay, and this number, the only thing to keep in mind is that it sort of drops exponentially in the number of samples that you end up taking. There's some other factors that sort of show up, but this is usually what you take away from this. I'm assuming that people have seen Chernoff bound somewhere, so I'm not going to actually prove it. But yeah, I would sort of highly recommend there's an article which is just called 5 proofs of the Chernoff bound. And they're amazing proofs. Like the first proof is a standard proof, which is the moment proof or something. And then there's one proof by Huatal. There is one proof by Cabinets and Impagliazzo. And then there's one proof that uses differential privacy. And so it's a really nice article to read.
5 proofs of the Chernoff.
Of the Chernoff bound. Yeah. Okay. So I will sort of highly recommend that people try out. But now, looking at this, this expression the Chernoff bound has, this immediately is going to tell us what should I choose t to be, so that this probability that I have here, this is at most delta. Okay, so what should t end up being here? And it's sort of easy to convince you. Just look at this expression and you basically know that you need t to be about 1 over epsilon squared log 1 over delta. Okay, then once you choose this, then this error probability turns out to be at most delta. So that's the random sampler. You query it at t locations where t is equal to this quantity, and just take the empirical average and output that. Okay, and like last time, something that we use to measure how well we are doing is how many queries did we make and how much random bits did we end up using. So the number of queries we made is like 1 over epsilon squared log 1 over delta. And turns out this is tight up to constants, and that you will need to make this many queries. But what is perhaps not clear is do we really need this much randomness? Do I need to use r times 1 over epsilon squared log 1 over delta, or can I get away with somehow a little less than this much randomness? Okay.
R was the domain size.
So R was, basically the function is on 0 1 to the R. I have a feeling I might soon change it to M. See, yeah, somehow changed it to M already. Sorry about that, but yeah, but whatever is the domain size. Okay. So now what we are going to do is try and come up with a way of sort of saying that, did we really need independent samples? Or can we get away with some limited independence? And then basically try to do the same thing. In the sense that try out many samples, take the empirical average and output it. It's just that I'm not going to expect these many samples to be completely independent. So I don't want to spend R random bits for every sample. I mean, that feels too wasteful. Okay, so that's what we're going to focus on. And so unfortunately, I've seemed to have switched from R to M. And I don't know how long this is going to go for. So let's say that the input domain is 0, 1 to the M now. So what we are going to do is we are going to build a hash function from 0, 1 to the K to 0, 1 to the M. Okay, this K is something we will soon choose, like what this is supposed to be. And we'll build some hash function. Oh, K is again a bad choice. Because I'm going to choose a K-wise independent sort of thing. Okay, no, maybe I'll stick to pairwise independent here or something. Okay, so I'm going to tell you what a pairwise independent sampler is. Okay, so here is what you do. You construct a pairwise independent hash family as required above for a suitable choice of K that you will figure out from this thing. Okay, and what you do is you pick a function from this hash family at random. That's your choice of randomness. After this, there's no randomness. Okay, and what do? You specify some y1 through yt that are distinct elements in your domain. You need t samples, you specify y1 through y2. Okay, this can be completely deterministic. You can just take the first t elements or something. Or maybe you set your k such that 0, 1 to the k is like t. So that you have t different things. Okay, and just take the output values for each of these, the h on each of these t elements. Each of them will give you an m-length string. Take the empirical average amongst those m-length strings. Okay, so let me just go over it again. The hash family is something where the input domain is some nonsense. The input domain has at least t elements. That's all you should care about. The output domain is 0, 1 to the n, which is the same thing as the domain of your function. Okay, and I want to think of the truth table of the hash function as my t samples. Okay, and what's the truth table of the hash function? You just choose your h and just evaluate this h at these t different points. So the randomness is coming from just choosing your hash function h. Okay, from this set. Just think of your t samples as being the evaluations of this hash function at these t points. And just take the empirical average amongst this. I hope the pairwise independent sampler is clear, like what you need to do. Okay, so from this sampler definition, the only thing we need for that K is that I want my input domain to have at least t elements. So I'm going to choose K to be equal to like log of t, whatever is the t that I need. Okay.
Where did t come from?
So t again, I need to sort of say what should I choose my t to be, so that this, like I want to say this empirical average is going to be within epsilon of the correct answer with probability 1 minus delta. That's what I want. Depending on some calculation I might now have to do, it will tell me that this t has to be at least something. And that t will indicate what my k is supposed to be. That is the k above. So
t distinct things.
I just need t distinct things. So k, think of k as log t. Whatever, if you need t samples, think of k as log of that.
Use the fully independent coins.
Huh?
Use the fully independent, the number of fully independent coins.
No. The coins are only with respect to the choice of the function h.
That's what you're saying by transferring, choosing t independent things.
So these are not independent. So in the sense that, like, I'm choosing a function h and then building t correlated samples. Okay, and it's just that those samples turn out to be pairwise independent. Okay, so rather than choosing t times m random bits to build these t samples, I'm going to expect randomness only to choose the function h and end up building t times I mean, T many samples from.
Why not use all elements of 0 power k? You are not using any extra.
Yeah. So I'm just going to set 0, 1 to the k such that 2 to the k is like T. That's the eventual setting of parameters. Okay. And it's just a question of I don't know what the right value of T is supposed to be. Okay. What should I choose T to be so that I have the concentration bound that I want? Previously, my T was determined by Chernoff bound. Because that told me that if you want to be within epsilon of the expectation with probability delta, then you need to set T to be 1 over epsilon squared log 1 over delta. Now, hopefully, there is a different bound that will show up here.
This is trying HGE.
Yeah, basically. So, okay. So, what I want is the following. I basically want to understand this. I give you a bunch of y1 through yt. Previously, these were independent. But now they are not independent. They are maybe pairwise.
Basic conversion. Was division independent? Oh, sorry,
I don't know.
should be.
So,
Interesting.
but I should also mention that Chernoff bound is apparently not by Chernoff. So there's a really nice, interesting history for that. I think Hofding probably had it like several years prior to like a more general, probably even Azuma. Anyway,
I have no idea. Azuma, etc. predated Chernoff.
Apparently,
Oh, I thought so.
there's a funny joke also.
Because the concentration inequality is learned in the reverse order.
Yeah.
Chernoff, Webbing, Azuma.
Yeah.
Robotics.
No, not the Lobachevsky. Anyway, so we are on YouTube, so I will I'll tell you later. Okay, so this is the question we want to ask, which is you're given a bunch of pairwise independent random variables. Again, let's say they're all like basically they're taking values in 0, 1. I'm basically trying to keep the hypothesis as similar to Chernoff as possible. Okay, and each of them take value mu. And I want to know what is the chance that the empirical average, maybe I should have written it as 1 over T times this or something, but it's the same thing. That summation yi deviates from mu times T by more than a factor of epsilon. Okay. Good. And for this, what we will end up using is the Chebyshev's inequality, which actually holds for any random. It's just going to be convenient to use it in this particular setup because of pairwise independence. So Chebyshev inequality is basically Markov's inequality that we apply after squaring. Basically, that's the thing. So what does it say? If y is any random variable, the probability that you deviate from the expectation by at least epsilon is at most the variance of your y divided by epsilon squared. Where, just to make sure we're all in the same place, the variance is just the expected value of y minus mu the whole square. And in fact, the proof of this is basically you just take y minus mu as a new random variable, y minus mu the whole square as a new random variable z, and just apply Markov on that. Okay. Now, okay, this is a statement that is true for any y. Why is it so special about trying to use it for sums of pairwise independent random? What are we going to gain here? And the reason is the following. So let's say that this y is equal to summation yi, I goes from 1 through t, where each yi was a pairwise independent. I mean, the set of y's are pairwise independent. Okay. Now, linearity of expectation will tell me that the expectation of y is just t times mu. This is not surprising. This is just true for any set of random variables. But what you get in addition is that the variance of y, this turns out to also be the sum of the variance of the y's. Okay? And all you need to do is just look at the
Use the pairwise.
this is because yi's are pairwise independent. Because yi's are pairwise independent, and in some sense variance is like a degree 2 calculation, things split up nicely, and what you end up getting is that the variance of a sum of pairwise independent random variables is just the sum of the variances. And the stupid bound you can give for the variance is that each of these yi's are some random variable between 0 and 1. So the variance can't be more than 1 for any yi. If you're a little careful, you can probably put a 1/4 also. But we are going to be very sloppy with respect to constants and sort of say something is between 0 and 1. So the maximum variance it can have is like at most 1. Okay. So therefore, this is going to tell me that the variance is at most t. All right. So what does this mean? This means that if I look at probability that summation yi is at least mu plus epsilon times t, I'm going to write it a little differently. I'm going to write this as okay, actually let me do it here itself. I want to pull the mu's inside. Y minus mu is at least epsilon t. Okay. Now, if y's are pairwise independent, then if I just translate them, they're of course going to remain pairwise independent. So by Chebyshev's inequality, this is going to be at most the variance of summation yi divided by epsilon squared t squared. Because Chebyshev inequality says the probability that a certain random variable deviates from its expectation is at most the variance divided by whatever. Okay. No, this one. Okay. And for what is the variance of summation yi? We just argued that that is at most t. So this is going to be, this is at most t divided by epsilon squared t squared. Okay. Unfortunately, 1t survives in the denominator. So you get 1 over t times epsilon squared. So this tells you that you still get some sort of concentration. This is it tells you that sum of pairwise independent random variables is still going to be very close to the expectation, and the probability decays as you move away. Just that it doesn't decay exponentially with the number of samples, but it sort of decays as the function of t, as a linear. All right. So now if you again ask, I want this quantity to be like at most delta, because that's my probability of error. Okay, what should I choose t to be for this to work? And looking at this expression, this should tell you that t should be like about 1 over epsilon squared times 1 over delta. Just to contrast this with what it was in the Chernoff setting, it was 1 over epsilon squared log of 1 over delta. But now t has to be much larger. It can't just be log of 1 over delta, it has to actually be 1 over delta. Okay, so now we are at a good position to sort of contrast what's going on. So previously the number of queries was 1 over epsilon squared 1 over delta. But now the number of queries is 1 over epsilon, log 1 over delta, but now it's like 1 over epsilon squared times 1 over delta. So the number of queries has actually gone up. Previously we used to make far fewer queries. Now we are making a lot more queries. But where we seem to gain is the amount of randomness we end up using. So the number of random bits previously was m times whatever was the number of queries. But now let's ask ourselves, how many random bits do we use now? Yeah, so it's going to, if you do this calculation correctly, what you end up getting is m plus log 1 over epsilon plus log 1 over delta.
It is 2 log 1
The 2, etc. I'm putting it in the order. I don't care about the constants. But basically, I need this many samples. So my k has to be set in such a way that k is at least this much. And the size of the pairwise independent hash family was something like twice m plus this. Or something. So that's why you get m plus log 1 over epsilon plus log 1. So in terms of randomness used, we have somehow decoupled the dependence between m and epsilon in some sense. So we seem to have gained a lot in terms of the randomness we are using. We are super efficient when it comes to randomness. The amount of randomness required is far less, but the number of samples is a lot more. So it's something, if you think of the sampler as an algorithm, it's like you're using less randomness, but you're running for more time. Because you're actually making a lot more correlated queries. It's just that the amount of random bits you're using to create these correlated queries is far fewer. Okay. Good. So all of these are these sort of samplers are also called averaging samplers. Because what is a sampler? At the end of the day, it makes a bunch of queries and it returns the empirical average. So these are called averaging samplers. But it feels a little puzzling because in the sense that what else can you do? Right? I mean, you're supposed to get an expectation. I mean, you're trying to somehow, how do I put it?
So you look at the product at the top of the number of queries and the number of random bits.
Yeah.
There you get like only log, I mean, you get 1 over epsilon square, 1 over epsilon to the 4, so there's a 4th part, and then there is a log 1 over delta, right? Whole square or whatever, right?
Sorry, I'm missing.
I'm just taking the product in the first two, product in the first two, and product in the second two.
Oh, that would be much larger because of the 1 over delta.
It's much larger.
Yeah. Yeah.
So is it possible to?
No, but why are we comparing it with the product? I mean, in the sense that I'm using this many random bits to generate a lot of correlated samples. I'm generating this many correlated samples, and that's what I take my empirical average over. So it's not like I'm using this times this many random bits.
No.
Yeah.
Suppose you want to optimize over the number of random bits as well as the number. Is there a trade-off?
So what we will eventually, I mean, hopefully in maybe another, I don't know, 4 lectures or 5 lectures, we'll actually achieve the best of both worlds.
You can do expander work that will give an.
Yeah. So once we see expanders and so on, we will actually see that you can get this many queries and this much randomness. So that's going to be something that we will go towards. And and so in fact, that is also going to be one of these things that example is actually not going to be an averaging sample. So we will see an example of a non-averaging sampler that does substantially better. In fact, I think at the moment, the best sampler we know of that achieves the right number of queries and randomness is actually a non-averaging sampler. And
what's the definition of an averaging sampler?
Sorry?
What's the definition?
The definition is just any algorithm that makes some bunch of queries, possibly correlated, and returns the empirical average as its output. That's an averaging sample. But if you decide to sort of say that, no, I'll make a bunch of queries and then carefully select a subset and then return the empirical average only on that subset or something, then you're doing something more than just returning the average.
So in general, you do some set of queries and return some.
Yeah, in general, you could return some function of your queries. But an averaging sampler is one that just returns the average of the queries in it.
And all samplers non-adaptive?
In fact, the expander sampler is not non-adaptive. I mean, it's not non-adaptive on the outputs, but actually, I don't know how to.
The expander sampler is non-adaptive. It just takes a random of standard.
No, but what is the adaptive? The queries are correlated. No, I guess Srijanto's point is like, do you look at the function output and then make a different decision? That you don't. Yeah.
But which point you queried?
Yeah, that is going to be.
Which previous point you queried?
By non-adaptive, I mean, it does not depend on the output.
Actually, I don't know of any sampler that makes use of what output it's on. But so with respect to samplers, also there is a really nice write-up by Oded Goldreich, which is called a sampling of samplers, where it talks about various things that in the build-up of these samplers, etc. Okay, so in problem set 1, you will see one example of a non-averaging sampler, and it's a rather powerful example. It's, you might have seen it in other contexts. It's something called the median of averages. It's a really powerful idea, and it's like you'll see one version of it. It won't quite achieve the best of both worlds, but you'll improve on some of the parameters. And once we see the next module, which is expanders and so on, we'll then be able to achieve it. Okay. So I have about 8 minutes left. So I'm just going to give you, got confused, are the YIs in the sampler pseudocode different from the YIs in the analysis? Oh yeah, I may have used the same YI. Yeah, I'm sorry. So these YIs I'm not thinking of as the same YIs in the analysis. In some sense, these YIs are like what happens with, I don't know, with respect to those, the hash function outputs. I mean, because the yi's in this question, etc., are random variables that take value 0, 1, whereas the yi's in the pseudocode are like elements in 0, 1 to the k. So they're not quite the same. I ended up using the same symbol for both of them. Okay, so to try and sort of segue into the next module in some sense, I'm going to start looking at, try and abstract out samplers as just graphs and sort of get a sense of, writing, okay, does k greater than 2 independence help, and maybe we'll get good. So hold that thought, because that is one of the questions in the problem set. Oh, okay. Yeah. So yeah, one of the questions in the problem set is actually going to be to use higher independence and sort of see, do you get advantages, and at some point do these returns start diminishing, etc. And after the problem set, I'll answer that question. Hopefully you will all answer the question. Yeah. So I want to look at these samplers as just graphs, okay, that have a so I'm going to think of, there is some n elements on the left, and then m vertices on the right. And sort of, I'm going to assume that this graph is sort of left regular. Okay. And let's say the degree is like some small t or something. Okay. And the semantics that I want to have in mind is like, I should think of this n here as the random coin process. Okay. And this is in some sense the function domain. That is, if I'm trying to build a sampler with respect to functions on 0, 1 to the m, 0, 1 to the m is what shows up on the right hand side. And the left hand side, basically, this is your bag of functions you're going to deal with. Or if you think about it from sampler's perspective, whatever is the random coin tosses you need to do in order to build your t samples. Okay. So every vertex on the left corresponds to one instantiation of coin tosses. Okay. And these, the t neighbors are the t samples that this algorithm is going to eventually take an average of. Okay. So this is just averaging samplers, just written down as a graph. Okay. Good. And in order to get a sense of, is this a good sampler? Is this not a good sampler, etc.? I'm going to define a certain notion, and it's a notion that we'll deal with throughout this course. Okay, because every time we see a new object, we will try to write down the same thing and just notice that, oh, they're all basically the same thing we are trying to study. Okay, so now given a function, which is some capital F, which is like one of the things that the sampler is supposed to estimate. Okay, and a parameter epsilon, I'm going to define a certain bad set. Okay, so bad epsilon of f, this is going to be the set of all x on the left, such that if I look at the empirical average of all the neighbors of x and compute f of x, like this is what the algorithm would have returned had you started out with x as your random bits. Then it will basically look at the t neighbors and then return the average there. I want to know that this average is bad, the sense that it actually deviates from the expectation too much. So this is greater than mu of f plus epsilon. That is, I want to say, with respect to the function f and with respect to the target accuracy.
Plus minus, right? I mean,
right now I'm doing it for just less than, because the requirement will work for all f. Okay.
So you can replace f by minus f.
F by minus f, and that should. So basically, this is what the bad set is. This is the set of bad coin tosses. As far as the algorithm is concerned, if it was given this function as input and this was the expected accuracy. Okay. And when is a sampler a good sampler? I mean, something is a delta epsilon sampler if for every choice of your function f, this back set should be a small set. That is, it must only take up a delta fraction of the possible random counts. Right? So basically, if the choice of the left vertex happens to be in the bad set, your algorithm will deviate from the expectation by more than epsilon. And I want to say the chance that I fall in this bad set is not too large. That is, no matter what function I care about, I want the size of this bad set to be at most delta times. Okay. So we will take this particular notion, and you can already start seeing that, if this function was sort of very spread out, like in the sense that if you pick up a random neighbor on the left-hand side and look at its neighborhood, if it more or less sort of touches many of these neighbors and it looks independent and stuff like that, it looks like this will be a good sampler. Okay. So in the next class, what we are going to do is we are going to basically, okay, actually I might take a small detour to look at something called almost k-wise independence, or I might push it to sometime later. But what we will start looking at is we'll start looking at samplers as graphs and ask ourselves, what are some necessary conditions that if I know that the graph has this property, it will just turn out to be a good sampler because of this property. So for example, one of the things that came up earlier was that, if you're thinking about building hash families, somehow building a good code was somehow very similar to building hash families. And we just saw that if we build a hash family, we got a sampler. So maybe some necessary requirement for building a code might already give us something like this or something. Or maybe there are some notions of pseudorandom graphs that we may be interested in.
So ABC codes will give rise to such.
Those are things, in the next module, what we are going to do is we are going to focus on pseudorandom graphs, which are namely expanders. And sort of say that, if this graph has very good vertex expansion properties, it will turn out to have good sampling properties. So that's going to be roughly the goal of the next module, where we start studying expanders. And many times we might be dealing with bipartite graphs and then looking at bipartite expanders. So, okay. So just take a minute more or something. So many of the different pseudorandom objects that we study, they will all have something to do with you have some bipartite graph and you want this graph to have good expansion. It's just that depending on the context you are looking at, this graph has different flavors, in the sense that there are certain situations where maybe you want n and m to be roughly the same, and you want the t to be like constant. That's the typical setup you are going to be dealing with when you're dealing with expanders. But maybe there are other situations where n is tiny but m is large. And maybe there are other situations where n is large and m is tiny, etc. So it's just that many of them, you might be looking at very similar properties of graphs, except that in some sense, the aspect ratio of this graph will be very different. But throughout, what we will try to do is keep coming back to this notion of bad set definition. And notice that almost every single thing that we are trying to study has some expectation about such bad sets. You want your bad sets to behave a certain way. And that is what will allow us to say, if you build one object, you often can build these other objects also. So we will sort of think of list decodable codes in this fashion. We'll think about, we won't be doing extractors much in this course, but extractors can also be thought of in this fashion, and so on. So many pseudorandom objects, there is a very nice unified view that we have, and we'll build them as we go along. Okay, sorry, I went a little over time.
That would be like y, the summation.
Oh, sorry, thank you. Thanks. Yeah, so this is f of y. That is, you take the average among all the neighbors. Yeah. Okay, and in the next class, we will slowly start moving towards expander graphs in general. Yeah, but it will sort of keep the sampler on the back, and every once in a while keep revisiting the samplers to get a sense of have we done better.
And do you have door box?
Yeah, we do. So I don't know if I'll be doing that in the class, but I'll, for example, Goldrex, the manuscript has. It tells you why is 1 over epsilon squared log 1 over delta the right answer when it comes to queries. Why is m plus log 1 over epsilon plus log 1 over delta the right answer when it comes to randomness, and so on.
The sampling of samples.
Yeah, it's called the sampling of samples. Okay.